Good afternoon, dear audience. My name is Anastasiya Lebedeva. My supervisor is Franciszek Herman. It's an honor for me to be the first speaker at this conference. Today you will hear various talks, and many of them are devoted to superconductivity, like transition between the superconductor and ferromagnet by Marcel Pollack, or the superconducting radio frequency cavities by Matu Zhelatki, and many others. Whereas our work will be devoted to gap behavior in Dynes superconductors. Let's begin with short introduction. We know that semiconductors have energy gap which determines its conductivity. Likewise, superconductors also have energy gap, but this time it is temperature dependent, means at a certain temperature the gap is zero and superconductivity stops. This certain temperature is called critical temperature. So the goal of our work is to find out as much as possible about the energy gap, how it behaves close to critical temperature, how it behaves close to zero temperature, how it behaves in some range of temperatures. So let's look at what we will use to achieve this goal. The first is the BCS-theory ratio, which connects the energy gap, which is delta 00, and critical temperature. How this ratio was achieved? It was achieved with the solution of the energy gap equation you can see here. But in BCS case, this parameter gamma is zero. Gamma is for pair break-in scattering. So it is zero in BCS case. It means that in BCS case, nothing destroys these Cooper pairs in superconductor. Well, we want to find as much as possible about the energy gap in a more general case, which is called Dynes case, where the gamma parameter is not zero. So something destroys these pairs inside a superconductor. So if we want to somehow solve this equation, but where these are some constants and we don't need them. We focus on the delta, which is for energy gap, on T, which is for temperature, and gamma, which is for pair break-in scattering. If we look at this equation, we see it is quite tough to explicitly have the equation for delta on T. That is why we have two possibilities. We either calculate this equation numerically or somehow try to find an analytical approximation of delta behavior. Well, if we want to solve this equation numerically, we will have to for arbitrary gamma and for arbitrary temperature, we'll have to use millions pairs of gamma and temperature and calculate delta explicitly for these pairs. And these pairs, it is a really large amount of these pairs, so it will be quite inconvenient and time demanding. That is why we try to find a better approach and find the analytical approximation of delta on T. So before we begin our calculations, I'd say that we will also at the beginning of any calculation, we will compare the energy gap equation in two cases. In BCS case, where gamma is zero, and in Dynes case, in general case, where gamma is not zero. And when I will say clean case, I will mean the BCS-theory case. So let's begin. The first step was to find such a relation between the BCS and Dynes gap. This equation is not a new, it is a known fact, but in our paper we exercise its derivation because the logic of its derivation is quite similar to what we'll have in the future. So what is this logic? We have energy gap equation for clean and Dynes cases, then compare them, make approximations where temperature equals 0 kelvins, and achieve such a result. From the introduction, we remember that when the gap is 0, superconductivity stops. So let's look at this equation. This gap is 0 when gamma parameter equals to delta 00 to 2. So it makes sense to look at this parameter gamma less than this value. And when gamma goes to this value, is close to this value, we call it the critical limit of gamma. We will use this equation later, and we will use the term of critical limit of gamma. So remember this term and move further. The second step was to find the analog of the BCS-theory ratio, because it is valid only for 0 gamma, and we wanted to find something like that in Dynes case. So again, we take energy gap equation in clean case, in Dynes case, compare them, make approximations for critical pair break-in scattering, means the critical limit of that gamma, and achieve such a ratio. Someone can say, well, this ratio is valid only at one fixed value of critical pair breaking scattering. What do we use it for? Well, experimentally, let's suppose we have a piece of semiconductor or a superconductor, and experimentally we can measure the energy gap and the critical temperature, and we can calculate the ratio. So, if the value of its calculated ratio equals to this value, we know that our superconductor has critical pair breaking scattering. If we've calculated this ratio and we've achieved such a value, our superconductor has 0 pair breaking scattering, and if our value is somewhere between these values, we can say that it has some pair breaking scattering, but it is not 0, and we can judge if it is closer to the critical gamma case or to the clean case. Okay, now let us compare these two values to find out how pair breaking affects superconductivity. We see that this value, this ratio, is higher than this ratio, which means that at critical pair breaking scattering, the critical temperature is suppressed to 0 a bit more than the energy gap. Okay. All the calculations before were made at fixed values, at critical temperature, at critical pair breaking scattering, and we said we want to find as much as possible about the energy gap. So that is why now let us solve the gap equation without any conditions on gamma or temperature. So we again take energy gap equation for clean case, for Dynes case, compare them, and achieve such a result. We've made no approximations on temperature, that is why this equation is valid for full range of temperatures. But we see that it is still complicated to find the explicit dependence delta on temperature. That is why we will solve this equation numerically and later use it to control our approximations. Well, some magic occurred and we've achieved such a result, but the logic of the calculation of such formula is crucial for our paper, so I really recommend you to look at it, to read it in our paper at least once. Okay, we have such an equation, and now let us look at such a ratio, such a dependence of the ratio, energy to gap ratio in Dynes case and in clean case. We know that it can be described by such a parameter, by such a coefficient r. We can calculate it numerically. So let's do it. We achieve such a result, that with increasing gamma, this coefficient r increases too. So what does it mean for us? It means that if we rewrite the equation in such a form, it means that the energy gap ratio grows faster, because it increases, than the temperatures ratio. So what we expect to see, if we draw the numerical solution, markers are for numerical solution of the equation we had before, we see that at the beginning, the blue line is for almost clean case. The temperatures ratio is 1, the deltas ratio is 1, 2. Now, let us increase our gamma, increasing gamma, and we see that the temperatures ratio is a bit less than 0.6, and the deltas ratio is a bit more than 0.6. So this ratio, this temperatures ratio tapers faster than the energies gap ratio. Okay, so with the help of the analysis of that R coefficient, we can say how the gap will behave depending on gamma. Let us move further. Again, we have our equation we will solve numerically to control our approximations. And now let us find how the gap behaves close to critical temperature. So again, we have energy gap equation for clean and Dynes cases. We compare them, we make approximation for temperature goes to critical, and achieve such a result. We've made approximation for temperature, so this equation is valid only for temperatures close to critical. Now, remember this equation, because we will rewrite it in such a form. Oh, no, we'll not rewrite in such a form. We've achieved such a result, and we want to check if it is correct. So the first step is to check if it is correct in BCS case, so where gamma is 0. So we use gamma equals 0 and achieve such a result, which is a well-known result of BCS theory, of the BCS theory. So the second approximation we will calculate is for critical limit of gamma. And we achieve such a beautiful result. Okay, now let us rewrite that analytical formula in such a form. Again, we can calculate this coefficient p numerically. So we calculate it and look how it behaves depending on gamma. We see decreases with increasing gamma. So what does it mean? It means that if we draw the dependence delta on temperature, we expect the slope of the function to flatten with increasing gamma. So let us look at this picture. The first thing we see is that markers are for numerical solution of our equation we achieved before, and lines are for the analytical formula. We see that in vicinity of critical temperature, the agreement is perfect. That is the first thing. And the second thing, with increasing gamma, the slope of the function really flattens. So again, the analysis of p coefficient allows us to quantitatively say how the gap will behave depending on gamma. And now, the icing on the cake, because at the beginning we said we want to find as much as possible about the energy gap. So our dream is to find an analytical equation for gap valid for full range of temperatures. And we know that there is such a trick in BCS theory that we approximate the gap behavior with hyperbolic tangent function. So we wanted to find out if something like that is possible for Dynes case. We tried to include these dependence on pair breaking scattering to this hyperbolic tangent function, and we've achieved such a result, where delta G is for guessed, because we've guessed such a heuristic formula, and if we calculate this formula, and markers are again for numerical solution, we see the perfect fit. The asymptote is good, the sharp slope is good too, but it is a little disagreement in this region of temperatures, but it is really small. That is why we can say that this formula gives quantitative description of gap behavior. It was not derived analytically, it was guessed. Nevertheless, it gives us the description of gap behavior in full range of temperatures. To sum up, throughout our work, we derive the Dynes ratio value at critical pair breaking scattering, which connects two parameters delta, energy gap, and critical temperature, which are experimentally measured independently. Then we derive the analytical equation describing the gap close to critical temperature, and we've guessed the heuristic formula given the qualitative, and I'd rather say quantitative, description of the gap behavior in full range of temperatures. Thank you for your attention. I'd like also to thank my supervisor for his patience and effort. I was extremely happy to share these results with you, and I'll be even more happier if you have some questions. So thank you for your attention.
Okay, thank you.